Hello, hello, hello. This is Nicholas, and I wanted to do just a quick video on a pretty cool fact in 3D. And the fact is let's say we're in 3 dimensions. Now, I'm not the best 3-dimensional drawer. And we have a plane in 3 dimensions. So, maybe I'll draw it in blue. Oop. So this is our plane. Sorry for the bad drawing, but I mean, hopefully you can imagine. This is the X, the Y, and the Z axis. So this plane is at an angle and going kind of above the Y axis. If you can imagine this, doesn't really matter so much. The imaginative part of it, I guess. But the idea is that if I were to zoom in on this here, we have a point on the plane. This is a point on the plane. Let's call it a generic point, X, comma, Y, comma, Z. Some generic point on the plane. And this is, say, another point on the plane, but this is a specific point that's given to us. And so it will be a number. We'll call it X naught, Y naught, Z naught. Maybe the point, well, this plane is going, this is in the positive direction, so say this is 2, and then maybe this is 1, 2, 3, and then maybe it goes up 1, 2. So maybe this point here is the point, it doesn't really matter what I call it, but maybe it's the point 2, comma 3, comma 2. See, because I go 1, 2, and then I go 1, 2, 3, and then I go on the z-axis up 1, 2, like that. Okay, ooh, I wanted to get rid of the dots. Okay, I'm really messing it up now. Okay, let me draw my axis back in. And let me draw the plane. Okay, so we can create a vector, right? Between these two lines, like this. We can create this vector. And so this vector, call it the vector, I don't know, p sub 1. And it's going to be the vector x minus x naught, y minus y naught, z minus z naught. It's going to be that vector. In other words, we take the generic point and subtract off the values for the specific point, because that would be this distance here. That would be the length of that vector. Now, let's say we have a vector normal to, or orthogonal to, or perpendicular to. They have 3 different words for the same meaning of at a right angle. So this vector, we call it we usually use the word normal. It's normal to the plane. It's perpendicular to the plane. So it's at a 90-degree angle to the plane. So I'm going to try to draw this the best I can, but it's popping out of the plane like this at a 90-degree angle to the plane. At a 90-degree angle to the plane. So, and let's call this the normal vector n. And let's say it has components A, B, and C. Then what this would mean is that if I were to dot vector n and vector p sub 1, I would get 0. Because remember the definition of the dot product, vector A dot vector B, is the magnitude of vector A times the magnitude of vector B times the cosine of the angle between the two. Well, the cosine of the angle between the two is 90, or the angle, well, first, the angle between the two is 90 degrees. So the cosine of the angle between the two is 0. So this whole thing is 0. So when I dot these two, I should get 0. This means that if I take A times x minus x naught plus B times y minus y naught plus C times z minus z naught, I'm going to get 0. And I can make this ax plus by plus cz is equal to ax naught plus by naught plus cz naught. And I'm going to call this whole part here capital D. So my planar equation, ax plus by plus cz equals D. That is the standard form of the equation of the plane. And notice that should make sense because remember the standard form for the equation of a line is ax plus by equals c. Oh, and by the way, why can I just call this all D? Well, because all of this schmozkin here is just a number. A is a number, x naught's a number, all of it's a number. So it can all just be one constant that I call D. So notice that the equation of a line is ax plus by equals c. And so we have one independent variable x. We put in an x value and we get out a y value, right? Here we put in an x. We have two independent variables. We put in an x, we put in a y, and we get out a z. And this would make sense, right? It takes 2 dimensions to describe a one-dimensional line. So it should follow that it takes 3 dimensions to describe a two-dimensional plane. And so notice, by the way that we built this planar equation, by the way we built it, that this A, this B, and this C are no coincidence. The coefficients of any planar equation give the components of the vector normal to that plane. And that's a pretty cool fact. So right away, if I gave you the equation 2x plus 3y